Good morning, my dear students. Once again, welcome to the world of electronics. Our lesson for today is all about power supply. Power supply is an electrical or electronic device that supplies current in an electronic circuits. Electronic appliances that contain electronic circuits, such as the television receiver, the DVD player, the satellite receiver, the oscilloscope, the multimeters, the electronic emergency lamp, the computers, the laptop, the cellular phones, the electronic washing machine, the inverter operated refrigerator and air conditioner, the robots, or any electronic equipment that are found in electronic industries are put into operations by means of power supply. Hence, power supply is a very important tool in electronics technology. There are three major types of power supply. These are the batteries, the linear mode power supply, and the switch mode power supply. The batteries are equipped with DC voltages, which are served as the power source to operate the electronic circuits. The batteries are the AA type battery that contains 1.5 volts. Okay, let us measure. We will set this one to voltmeter DC. And let us measure the voltage. Remember that battery is the source of the DC voltage that has fixed polarity. We have here the positive side. It is 1.6 volts. And it is labeled here on the surface of this battery. It is registered here or labeled here 1.5 volts. But since this battery is still new, we can register or we can measure 1.6 volts. Also with this AAA type battery, it is also 1.6 volts and it is labeled here on the surface 1.5. This double P 3 types battery, 9.5 volts. This is actually 9 volts and it is labeled here 9.5 volts or 9 volts. The battery of the cellular phone, it is 3.7 volts. A white cell battery, which is used by this emergency lamp, it is also DC voltage. If we measure the two terminals here, for the polarities of the battery, it is 4 volts, as it is indicated here. 2 amperes, 4 volts. DC voltages that are in these batteries are not dependent from the AC source of the outlet being distributed by the Soleco or Lieco company. By themselves, they can be installed right away in a certain circuit here, just like this. It has two AA battery. Then by themselves, they can operate the circuit. Whereas the other two types of power supply, the linear power supply and the switch mode power supply, are dependent from the AC source. That's why we have here, there is an AC cord. There is an AC cord to be connected to the outlet. So these two power supplies are dependent from the AC source. Without the AC source, it cannot provide desired level of DC voltages at the output. Okay? So for today's lesson class, we will give more emphasis on these two types of power supply. On what way that the desired level of DC voltages are processed by the two circuits. Also, we will be studying their pros and cons. The efficiency of the two circuits, to which of these two circuits is efficient and recommendable to use to the particular circuit. Okay, let us first have this linear mode power supply. A linear mode power supply is equipped with a transformer before it is processed by a rectifier circuit. Meaning to say, we have here an example of a linear mode power supply. We have here a transformer, which is here. It is connected to the AC source, to the outlet, that distributes AC voltage to the transformer. The transformer now is used to transform, to lower the voltage from 230 volts down to 12 volts. At it is necessary for the particular circuit. The electronic circuit probably needs DC or needs 12 volts, lower amount of voltage. Because 230 volts from the outlet cannot be directly fed to the circuit. So we need to transform it using transformer. Okay, we have here. Again, let us set this one to AC voltmeter. Then, press the select button in order that you can measure the AC voltage here. It is 230 volts. That is now the voltage being distributed by the Soleco company. Then, it is actually transformed by this transformer. It is lowered down into okay, let us measure it properly. It is 12.4 volts. It is now transformed. It is lowered down to AC. Remember that this is still AC. Okay, let us measure the AC volts using oscilloscope. Okay, it goes like this. Okay. It goes like that. Okay, let us measure. It is 12 volts. Remember that the voltage at the output of the secondary winding is 12.4 volts. Okay, this is now the waveform that is outputted by the secondary winding. The oscilloscope test probe actually, we have here, is connected to the secondary winding of the transformer. Okay, there are two terminals of this test probe. The test point 1, which is connected to the one of the terminals of this transformer, and the negative side is connected to the other terminal. So, the voltage there actually is 12.4 volts. But here, if we are going to count, let us compute. Let us click again. Okay. It goes like this, class. 0, positive, negative. 1, 2, 3, 4, 5, 6, 7. 7 centimeter times 5 volts. Here, the range is 5 volts. So, 7 centimeter times 5 volts over centimeter. Centimeter unit and centimeter unit are cancelled out. The remaining unit now is volts. So, 7 times 5 is 35 volts. It is actually the peak-to-peak value. From the peak of the positive alternation to the negative, to the peak of the negative alternation, the voltage there is 35 volts. That is now the peak-to-peak value. Then remember that the transformer output will operate only half of the cycle. That is the positive alternation and the negative alternation. Only one alternation will conduct at a time. Okay? So, peak value is equal to peak value over 2. The peak to peak now is 35 volts. Over 2 is 17. Let us divide. 35 divided by 2, 1. This is 2. 15 is 7. 17.5. The peak value now is 17.5 volts. From the peak of this positive alternation to 0 level. The same also with here. From 0 to this peak is 17.5 negative. Because it is the negative alternation. But remember that the measured voltage here is 12 volts. It is 12 volts. Okay. 12.4 volts. 12.4 volts is the RMS or the root mean square, which is the effective value, which is measurable now by our multimeter, DC voltmeter. The 35 volts cannot be measured by a voltmeter. It can be displayed only and measured by this oscilloscope. Okay? Actually, that 12.4 volts is just 70.7% of the 100% amplitude. So let us compute. So 12.4, because peak value is equal to RMS times 1.414. So RMS now is the measured value here, which is 12.4 volts. The measured value using our DC voltmeter times 1.414. So it goes like this, class. Okay. You have here 12.4 volts times 1.414 is equal to 17.5 volts. So we are right, because the peak value here based from the oscilloscope is 17.5, half of the cycle. And this 12.4 volts actually is the measured voltage here, the effective value, measurable by our multitester. And it is exactly correct, 17.5. Okay, it goes like that, class. Before it is rectified by these rectifier circuits. After being transformed by this transformer, it is then submitted to the two diodes that serve as a rectifier circuits. We have here. We have here the rectifier diodes. Okay. This rectifier diodes now will, from this voltage here, because the voltage at the primary is 200, okay, is 200, the RMS here is actually 230 volts, the measured value here, it is still RMS value, 230 also here. But the peak value here, if you are going to multiply 230 volts with 1.414, that will reach to 300 volts above. 300 volts above. No? Okay. Let us say 230 volts times 1.414 is equal to 325 volts. Actually is the peak value. 325 volts. From 0 level here to the peak of this amplitude is 325. Also 0 level to the peak of the negative alternation, it is also 325 volts, right at the outlet of this outlet. No? Okay. Now, it is now rectified by the diode. Then, let us try to get the signal outputted by that diode. So, it goes like this, class. Okay. It goes like that. Half wave only is being allowed to pass. Half wave. It is already DC, direct current already, but pulsating DC. Because if we are going to measure that using analog multimeter, we will set this one to 50 volts DC voltmeter. Because after diode, it is already DC. No? It is already DC. So we have here positive and negative. Okay? It deflects. Okay. Let us check. Check. Let us connect the one. Let us connect again the supply filter. Be sure. We have here the positive side over here, and the negative side is over here. There's something with the connection. Okay. But if it is reversed, it kickbacks. Meaning, it is already DC. It has fixed polarity already. Because once it is in correct polarity, the positive side is over here, and the negative side is over here, it deflects. It reaches there 16 volts. But if it is reversed, it kickbacks. Meaning to say, it has already fixed polarity, and it is DC. That is now the purpose of this diode, to rectify this AC into pulsating DC. How about the frequency, class? Set this one to hertz to measure the frequency. The frequency at the secondary winding is 60 hertz. You can notice, class, at the back of your TV receiver, the back panel, the rear panel of your TV receiver or DVD player, it is labeled there 60 hertz, 100 volts to 240 volts. 60 hertz there is the frequency actually. Then it is 60 hertz over here. Okay. I know, it is not. This one pala, sorry. Okay. The frequency here is 60 hertz. But at the output of this diode, the frequency is 120 hertz. Why? The frequency is doubled. Because this is full wave rectifier diodes, wherein the 60 hertz here is doubled at the output of this diode. Full wave. There are 120 pulses in 1 second. It is still varying. The voltage here is 0, 12, then probably 8, 12, 8, 12. There is a gap of 6 volts. Oh no, 4 volts variation. So, once it is supplied to a certain amplifier, there are musics that you can hear, but it is accompanied with hum. That hum now is the 120 Hz, which is audible to the human ears. Because frequencies ranging from 20 Hz to 20 kHz are audio frequency, which are audible to the human ears. Beyond that frequency is ultrasonic frequency, can no longer be heard, or it is no longer normal to the human ears. But 20 Hz below can no longer be heard also by the human ears, or it is no longer normal to the human ears. We call them infrasonic, and above is ultrasonic. Since 120 Hz is within the audio frequency range, it is audible to the human ears, but you can hear that as hum. Hum. A louder hum, because there's a variation of 6 volts. 12, 8 out. 12, 8, 12, 8. A matter of 4 volts variation. So we need to smooth out that using a capacitor to smooth out or to filter out that variation of voltage to eliminate hum. So let us connect this filter capacitor. Just across here, and let us get the frequencies of the signal. Okay, let us connect. Sorry, there's something wrong. Okay, there's something wrong. Probably it was okay, the capacitor was inverted actually. We mistakenly connect the capacitor because this side here at the input of this IC is positive. We happen to connect the negative side. That is a very good experience, class. There is an evidence that once an electrolytic capacitor, which is polarized, is inverted in a circuit, it will explode. Okay? Okay, we will change this one. We still have one available capacitor. Okay? Let us be certain with the polarity. Okay, we have here the positive side over here. And the negative side should be here. Okay? Should be here. Okay. So, the capacitor now, which is electrolytic capacitor, polarized because with positive and negative, is now connected properly. Okay? Let us connect this one again. Okay. So, let us connect the oscilloscope to determine the, it goes like this na, class. So, it is going like this. Okay, where is the, okay, we have here. This capacitor now will smooth out the pulsation. So the output across capacitor goes like this. So the variation now is smooth out. A while ago, at the output of the rectifier, it is 12, 8, 12, 8. A matter of 4 volts variation. It is a louder hum that you can hear. But with capacitor, the voltage is increased also. It reaches to the peak value. If we are going to measure the voltage using this DC voltmeter, the voltage across capacitor is 16 volts. 16 volts, class. 16.3. Whereas here is 12.4. AC. 12 volts, 12.6 volts. AC at the output of the secondary winding. But after it is rectified and filtered out by a capacitor, it increases to 16.3. Because capacitor is not only used to smooth out the pulsation to reduce the hum, but also it increases the voltage up to the peak value. It reaches to the peak value. It is 100% of this amplitude. So, it almost level with the AC waveform at the secondary. But it goes like this. There is still a variation. A little amount of variation. Probably 16, 15. A matter of 1 volt variation. You can hear music once this is supplied to an amplifier. But there's a little hum. Because the voltage is changed to 1 volt only. From 4 volts variation is changed to 1 volt variation na lang. Then finally, this circuit here, which is enclosed with invisible line, belongs to the regulator circuit, wherein a variation of the voltage here is held constant at the output. Held constant. If possible, if it is pure DC, it is 0 Hertz because there is no more variation. But it is not purely purified or regulated. Because the purpose of this regulator is to provide a constant output voltage despite of the variation at the input. Okay? Okay. Let us now explain how this regulator circuit operates. Okay? It goes like this, class. It goes like this. There are actually circuits here that play important roles in regulating the voltage at the output. We have here a transistor that serves as a regulator. Then, a feedback line over here, which is a sensor. This circuit senses the change of the voltage at the output, which will be submitted to the comparator. The comparator now will compare the feedback voltage. If there is change of voltage here, that will be feedback or feed to the comparator. Input line is base. On the other hand, emitter is connected to a Zener diode that provides reference voltage. Then, it is now submitted to that change of voltage will be submitted to the it is used to control the operation of this series regulator. By the way, it is called series class because it goes like this, class. Okay. Okay. It is series because we have here the filter capacitor. Then, the transistor goes like this, class. Then, we have here the two resistors. Feedback line. 4.7 key, 4.7 key. Then, the voltage here. Across collector and emitter. So, the output voltage is taken here. It should be 12 volts always. The voltage between collector and emitter is prone to variation in accordance with the change of the voltage at the input line, which is at this capacitor. A while ago, that was 16.2 volts. Alright, let us try to have only 16 volts. So, collector and emitter junction will drop 4 volts because the output voltage that is supposed to be the voltage at the output regulated is 12 volts. 12 plus 4 is 16. Okay. If the voltage changes higher, let us say the voltage at the outlet is increased. No? Let us try to use AC. AC volts. Change to AC. And measure the voltage here. It is 231. Let us try to increase the voltage to 240. 240, just like that. There are times that the voltage at the outlet increases from 230, it increases to 242. No? Okay. Let us try to measure the voltage across capacitor. The voltage across capacitor is 17. A while ago, that was 16.2. At the voltage here at the outlet is 230. Now the voltage at the outlet is increased to 244. The voltage also across capacitor increases. It increases. So when this increases to 17 volts, because of the increase at the outlet from 230 increases to 240, the voltage across at the output should be remain 12 volts. So what is changed now is this one here. This will be changed to 5 volts. 12 plus 5 is 17. But there are times that the voltage decreases also. So let us decrease the voltage. Change to AC again. And measure the voltage. Let us try to decrease the voltage to 204. From 230, it increases to 240. Now decreases to 204. Okay, let us try to measure the voltage across capacitor. Across capacitor now is DC volts. It is 14. A while ago, that was 16 volts across capacitor. When the voltage at the outlet is 230. When it was increased to 240, the voltage across capacitor is increased to 17 volts. Now it is decreased to 200 only, 210 at the outlet. Okay, let us try. 205 or 204. The voltage also across capacitor will decrease. It decreases to 14 volts. So, despite of the variation at the input, because the voltage across capacitor is dependent from the voltage at the outlet, there are times that the voltage at the outlet increases, decreases for every now and then. So, despite of the variation here, the voltage at the output of the regulator retains constant. Despite of the variation here, what is varied is across this collector and emitter. Collector and emitter of this transistor. Here. It is called series because this collector emitter junction is connected in series with these two resistors. But we are getting the voltage output across these two resistors. In what way that the voltage is varied here? Because it goes like this, class. When the voltage increases, the voltage across these two resistors should be 6 volts and 6 volts. 6 volts, 6 volts. All in all is 12 volts. The reference voltage of the general diode should be 6 volts. Okay, because it is going to compare the reference and the sense or the feedback voltage. Let us assume that the voltage increases from 12 to 13. So there is a change of voltage here. It is more positive. Let us say 6.5 volts over here. Because 13, 6.5 and 6.5 is 13 volts. So 6.5 feed to the base and the reference voltage is 6 volts feed to the emitter. They are being compared and there is a difference. It is more positive. Since base is positive, because NPN, this transistor conducts more. Conducts more because increases the voltage to more positive. So this transistor will conduct more. The operation of this transistor will be pulled down because the resistance between collector and emitter is lowered because it becomes hot. Once the transistor is conducting more, the resistance between collector and emitter here of this comparator is lower. Putting the base here, NPN, positive base, NPN, putting base to the ground. So this transistor could no longer operate at pole swing. So when it is cold, because it is not operating very well, as it is being reduced by this line, base is now almost connected to the ground, negative, base is positive. So this transistor is not operating very well at pole swing. So the resistance become higher. So if this is 12 volts, the voltage here is, let us say, 17 volts. This should be 5 volts. The voltage here is increased to 5, from 4 to 5. Why? Because the resistance here is getting higher. The higher resistance, the higher the voltage drop across this collector and emitter. Because this transistor is operating at pole swing. It is very hot. Putting the base current lower because it is connected to the ground, negative. So the resistance is getting higher. The transistor now is weak. But when the voltage is decreased to 15 volts, 16 to 17, then 17 to 15, the voltage here should be 3 volts. Because 12 plus 3 is 15. In what way that it becomes 3? Because it goes like this, class. This should be 12, this should be 6 volts, this should be 6 volts. And this is 3 volts, making it 15 volts. 3 plus 6, 9 plus 6, 15. But now, the voltage here is, let us say, 11 volts. This should be 5.5, 5.5, making it 11. So, the reference is 6 volts, and this is 5.5. It is now since detected by this comparator to the base. 5.5, 6 volts. It is negative. Negative now because lower. Base is positive. So, it reduced the operation of this transistor. Unlike a while ago, it conducts very more. It conducts more. Now, it conducts less. Because the voltage is lesser. So, this transistor is not operating. The resistance between emitter and collector is getting higher, making this transistor operating at pole swing because base positive is no longer connected to the ground. Once it is operating at pole swing, it becomes very hot. Once it is very hot, the resistance between collector and emitter is getting lower. It is getting lower. Once it is getting lower, the voltage drop here is getting lower also. So, this is with 12 volts, it becomes 3 volts. 3 plus 12 is 15. That is the way how regulator circuit is operating. This is just a basic setup of a discrete circuit. Discrete because it uses individual components. Unlike this power supply, using IC, we have here IC, integrated circuit. This is discrete circuit because the regulator circuit uses individual components. We have 2 transistors and we have 4 resistors with 1 general diode. But here, integrated circuit, because the complete circuit is already encapsulated in one housing. We call it integrated circuit. Okay. So, this kind of voltage regulator is not efficient because there is no temperature stability. It is very hot. The transistor power here is very hot. There is overheating. And there is no line regulation. There is no proper regulation at the output. The voltage here is not held constant as 12. Sometimes it is 12.5 or 11.5. There is a little amount of variation here. So it is not efficient. So it is now replaced with IC. We have here IC actually. Okay? So let us pause a minute before we will proceed to this regulator. Okay? Okay.